Hey kids, welcome to section 6.4, the normal approximation to the binomial distribution. Today we're going to learn how to use the normal approximation to compute probabilities for a binomial variable. So remember, we have talked about the binomial distribution before, and now we've talked about the normal distribution. So a normal distribution is often used to solve problems that involve the binomial distribution, since when n is large, like 100, the calculations are too difficult to do by hand using the binomial distribution. Remember that a binomial distribution has four characteristics. One, there must be a fixed number of trials. Number two, the outcome of each trial must be independent of the other outcomes. Number three, each experiment can only have two outcomes or outcomes that can be reduced to two outcomes. And finally, number four, the probability of success must remain the same for each trial. So if we are to follow those four characteristics of binomial distributions, the calculations can get pretty messy if you've got a large number of values. So therefore, we're going to try to use the normal approximation. So recall that a binomial distribution is determined by two things, n, which is the number of trials, and p, which is the probability of success. So when p is approximately 0.5, and if the n increases, the shape of the binomial distribution becomes similar to that of a normal distribution. The larger the n is, and the closer p is to zero point 0.5, the more similar the shape of the binomial distribution is to that of a normal distribution. But when p is close to 0 or 1 and n is relatively small, a normal approximation is inaccurate. So, as a rule of thumb, statisticians generally agree that a normal approximation should be used only when n times p and n times q are both greater than or equal to 5. So, in addition to this new condition, we also have something called a continuity correction that can be used. And this continuity correction is a correction that is used when a continuous distribution is used to approximate a discrete distribution. So, a binomial distribution is discrete, but if we want to think of it as a continuous distribution, then we can use a normal approximation only if we use this continuity correction. Also, remember from previous chapters that the mean of a binomial distribution is equal to n times p, and the standard deviation is equal to the square root of n times p times q. Now, these continuity corrections can be found in this table, as well as a procedure for using the normal approximation to the binomial. Step one, check to see if you can use the normal approximation. Step two, find the mean and standard deviation. Number three, write the problem in probability notation using X. Number four, rewrite the problem using the continuity correction factor. Step five, find the corresponding Z values. And then step six, find the solution. So basically, we have a little bit more going on in this problem. We have these continuity corrections. We also are not going to be given the mean or standard deviation right away. We're going to actually have to figure out what they are. So notice in this table that when we're finding the probability of x equaling a, we can't actually do the binomial distribution right away. So if we want to use the normal approximation, we're going to plus or minus 0.5 to both sides of that value so that we can try to capture what it is when it actually equals something. If the probability of x is greater than or equal to a, notice it's going to stay greater than, but we're going to back up a little bit to the left so that we can include that equal to part. If we're finding the probability that x is greater than a, we're going to add 0.5. If x is less than or equal to a, we're going to add 0.5 but still go left. If our x is less than a, we're going to still go left, but we're going to subtract 0.5. Again, these values are going to become easier once we start practicing them. So let's take a look at an example. A magazine reported that 6.6% of American drivers read the newspaper while driving. If 300 drivers are selected at random, find the probability that exactly 25 say that they read the newspaper while driving. Okay, so notice that this is a binomial distribution. We have a p-value of 6%. We have an n value of 300, and we're looking for exactly 25. So first, let's calculate what our mean and standard deviation are. So our p-value is 0.06. Our n value is 300. So our mean is equal to n times p, which is 300 times 0.06. That's going to give me 18. My standard deviation is the square root of npq, which is the square root of 300 times 0.06 times 0.94. If I calculate this and round to one decimal, we get 4.1. So I want to find the probability that x is exactly equal to 25. Well, according to the binomial and the normal approximation, this is actually going to be the probability that my x value is between 24.5 and 25.5. So when I draw my picture, my my mean is going to go in the center, 18, and my 24.5 to 25.5 is going to look like this. So I'm going to calculate two z-scores, one z-score for 24.5 minus the 18 over 4.1. And then I'm going to find my z-score for 25.5 minus 18 over 4.1. If I do my first z-score, the calculations give me a z-score of 1.83. If I do my second, I got those backwards. My first z-score here, 24.5, is 1.59, and my second z-score is 1.83. So my probability, if I look up on my z-score table, I need to look up 1.83, and that's going to give me 0.9664. If I look up my second z-score on my table, that's going to give me 0.9441. If I subtract those, I get 0.0223. I would expect my probability to be slightly lower because I am looking for exactly 25. That's a pretty small window of probability. So having a 2% chance that it's exactly 25 doesn't really seem all that unlikely. Okay, let's take a look at the next problem. 10% of Americans are allergic to ragweed. If a random sample of 200 people is selected, find the probability that 10 or more will be allergic to ragweed. Okay, so my p-value in this case is 0.10. My n is 200. My mean is going to be 200 times 0.10, or 20. My standard deviation is equal to the square root of 200 times 0.10 times 0.90. That's going to give me 4.2. I'm looking for the probability that x is greater than or equal to 10. This means with a continuity correction that I'm really looking for x is greater than 9.5. So on my graph, if I put the mean in the center of 20, then I'm looking for 9.5 and greater than. So to find my z-score, I'm going to take 9.5, subtract 20, and divide by the standard deviation, which is 4.2. This is going to give me a z-score of negative 2.50. My probability, since I'm shading to the right, is going to be 1 minus. I look up negative 2.50 on my z-score table, and I get 0.0062. So when I subtract from 1, I get 0.9938. So basically what this is saying is there is a 99% chance that if I randomly sample 200 people, I will find 10 or more to be allergic to ragweed. All right, let's take a look at the next example. If a baseball player's batting average is 0.320 or 32%, find the probability that the player will get at most 26 hits in 100 times at bat. Well, my 100 times at bat is going to be my n. My probability of a success is 0.32. So I can find my mean number of hits by doing 100 times 0.32, which gives me a 32. My standard deviation is equal to the square root of 100 times 0.32 times 0.68. This is going to give me a standard deviation of 4.7. I'm looking for the probability that my x value is at most 26, so that means less than or equal to 26. So continuity correction tells me that my x value is less than 26.5. If I draw my picture, I can put my mean 32, and then 26.5 less than would be to the left. My z-score is 26.5 minus 32 divided by standard deviation, which is 4.7. This gives me a z-score of negative 1.17. I looked this up on my z-score table. I'm shading left, so it is my answer, 0.1210. So if I look at 100 at-bats, I have a 12% chance that the player got at most 26 hits. Okay, so let's compare the binomial to the normal. So when n equals 10 and p equals 0.5, use the binomial distribution table to find the probability that x equals 6. Well, we never use the binomial distribution table, we just use the function on our calculator. So the probability is going to be the binom PDF. That was the button that we used on our calculator. And then the things went in the parentheses in alphabetical order. So we had the n equals 10, we had a p of 0.5, and we had an x of 6. If we type this into our calculator and hit enter, we get 0.2051. All right, now we're going to calculate this using the normal approximation and see how close we get. So now our normal approximation, our n is 10, our p-value is 0.5, our mean is 10 times 0.5, or 5. My standard deviation is the square root of 10 times 0.5 times 0.5. That's going to give me 1.58. Or 1.58. You can say 1.59. It's not that big of a deal. Okay, I'm looking for the probability that x equals 6. But if I use the normal distribution, I'm going to use 5.5 to 6.5. So that's going to give me a picture. If I put 5 in the center, 5.5 to 6.5. So I need two z-scores. One z-score is 5.5 minus 5 over 1.58. That's going to give me a z-score of 0.32. If I find the z-score for the other side, I get 6.5 minus 5 over 1.58. That's going to give me a z-score of 0.95. If I look these values up on the table and do bigger minus smaller, 0.95 on the z-score table is 0.8289. If I look up 0.32 on the z-score table, I get 0.6255. This gives me a difference of 0.2034, which if you compare 0.2034 to 0.2051, that basically is only 0.2% of a percentage off. So it is a very good approximation. if given the right circumstances. Okay, now we come to our application problem. Assume one of your favorite activities is mountain climbing. When you go mountain climbing, you have several safety devices to keep you from falling. You notice that attached to one of your safety hooks is a reliability rating of 97%. You estimate that throughout the next year, you will be using this device about 100 times. Answer the following questions. So, number one, does a reliability rating of 97% mean that there is a 97% chance that the device will not fail any of the 100 times? And the answer is no. We do not know that there's a 97% chance of failing during those 100 times. We know that the device will not fail 97%. So we only know that the device will not fail 97% of the time. We have no idea if it's if that means it's going to fail 97 of 100 times. We just know on average that it will not fail 97% of the time. Okay, so the next question, number 2, says, what is the probability of at least one failure? So remember, if we want the probability of at least one failure, we can do 1 minus the probability of no failures. And that means we could do 1 minus. Now remember, each of the failure percentages is independent of the other ones. So I can do 0.97 to the 100th. 100 tries, 97%. If I do this, I get 0.9524. So there's about a 95% chance that we're going to have at least one failure. It's not perfect. Number 3, what is the complement of this event? The complement of at least one failure is no failures in 100 climbs. So the complement is no failures in 100 climbs. And that's what we used when we calculated number 2. Okay, number 4, can this be considered a binomial experiment? Well, there are 4 things that we need to check. First, there are 2 outcomes. We have a success and we have a failure. The second criteria is that we must have a constant success probability, and we do. We have a constant probability of success of 97%. So we have constant probability of success, and that's 0.97. We also have to have a fixed number of trials, which we do. It's 100. Fixed number of trials. And that's 100. And then we also have to have independent trials. And each safety hook is independent of another safety hook. So we have independent trials. So we meet all 4 of the conditions. So yes, we can consider it a binomial experiment. Number 5, can you use the binomial probability formula? Why or why not? You could use it, however, it's going to be messy. The reason why it's going to be messy is you're going to be calculating up to 100 different calculations, and that can get really involved and confusing. So yes, you can do it, but it's going to be messy. Number 6, find the probability of at least 2 failures. So the probability of at least 2 failures is going to be 1 minus the probability of no failures plus the probability of 1 failure. And this is going to be all in a square bracket. So if I want the probability of no failures, that's going to be 0.97 to the 100. If I have one failure, that's going to be 100 times 0.97 to the 99 times 0.03 to the first. So if I calculate what's inside of the square brackets, 0.1946. If I subtract this from 1, that's going to give me 0.8054. So there's basically like an 81% chance that we're going to have at least 2 failures. Ew, I don't think I'm going to go climbing. Okay, can you use a normal approximation to accurately approximate the binomial distribution? Why or why not? Well, in order to do this, we need to check to see if NP is greater than or equal to 5 and NQ is greater than or equal to 5. That was one of the conditions in order to be able to use the binomial distribution. So my N was 100, and my P is 0.97. So 100 times 0.97 gives us 97, and that's greater than or equal to 5. 100 times, well, if my P is 0.97, my Q is 0.03. If I do this, I get 3, which is not greater than or equal to 5, so the answer is no. Is a correction for continuity needed? The answer is no, because we can't use the binomial, or because we can't use the normal approximation. No, because we only need it for the normal approximation to the binomial distribution. And since we are not using the normal approximation, we do not get to use a continuity correction. Number 9, how much safer would it be to use a second safety hook independent of the first? Well, the probability of one failure is 3%, or 0.03. The probability of 2 failures is 0.03 to the second power, which is 0.0009. So we go from 3% to a 0.09% safety rating. All right, kids, that's section 6.4. If you've got any questions, please let me know. And as always, keep calm and keep trucking.